Today we're going to be discussing section 10.6, which is about parametric equations. We're going to start by talking about what a plane curve is. So to talk about that, we're going to think about the motion of an object, maybe a marker, maybe a football, something else that's being thrown across a room. So if you think about, you take that marker, you take that football or basketball, and you throw that object, it's going to travel in a parabolic motion, parabolic direction. And there's a couple different ways that we could write that equation, that we could represent that relationship. The first one is our standard rectangular equation. So we use your x, you use your y, you set this equation, you can see that this is a parabola, it's opening downward just like we would expect to follow that motion of that object being thrown. This is great, except it does have some limitations. This will give me a corresponding x and y value, where x represents that horizontal distance from where you've thrown it, and y is the vertical distance from where you've thrown it. So it gives us how far we've thrown it horizontally and how far it's traveled up and down vertically. It has no connection to time, though. If I want to introduce something that says, okay, at time 1 second, where is my location? There's a couple ways I can do it. One is by writing this still in a rectangular equation, so still using two variables, but connecting time to height. And if you are in physics now, or if you've taken physics, this might look familiar for how you get to it. We're not going to talk a whole lot about getting to this equation, but this gives me, okay, after 1 second, I can figure out how high my object is based off of, what's the vertical change, what's the height there. And that's also great, but the issue here is this doesn't give me any horizontal change at all. It just gives me a vertical change with my time. So what a plane curve can do and what parametric equations can do is they can sort of combine both of these. And by introducing a parameter t, so t typically stands for time, it doesn't always have to, it depends on the situation. But we have a parameter t, it could be theta, it could be whatever we want it to be. But we can introduce this parameter t and we can create what's called parametric equations, which connect our x and our y values together. So looking down here, I've got this rectangular equation, the standard parabola equation. And then down below, I have parametric equations. I have two of them. And so when you do a parametric equation, so you're always going to take your one rectangular equation and produce two parametric equations. One that represents your x value in terms of our parameter t, and one that represents our y value in terms of our parameter t. So now x and y are no longer connected to each other, but rather they're both connected to a parameter value t. This is nice in that it gives me, okay, after a certain amount of time or after a certain t value, what's the horizontal distance? And after a certain time, after a certain t value, what's the vertical distance, the y value and the x value, and it pairs them together. So looking at this graph here, I have a parabola, I still have that parabola, and at each of these points that are labeled, I have the x, y values, but I also have a t value that corresponds with that. So if I look at the origin here, that is the x, y value 0, 0, but that matches to t equals 0. Because if I were to plug t equals 0 into both x and y equations, I get 0, 0 back. So I can, build a little table, t, x, y, when t is 0, x is 0, y is 0. And then using, this height time equation, I can figure out what's the time here when we get back down to a vertical height of 0. And that gives me, this beautiful t value of 3 root 2 over 2. My x is 72 and my y is 0. So now I have these three values that correspond together. Okay, and we're going to practice writing. We're going to practice dealing with the rectangular and parametric equations a little bit later. But first, what we're going to do, and this slide right here is just talking again about that connection between our t values and our xy coordinates. Okay, so this one, We've picked a slightly nicer t value, t is equal to 1. We get a slightly uglier xy value, but it's still a point on our parabola. If we were to graph that point, it would be on our parabola somewhere. So right now we have the definition of a plane curve. So a plane curve is essentially any curve that we can rewrite into two separate equations, one for the x and one for the y, both in terms of the same parameter variable t. Okay, so x and y are continuous functions of t, and the resulting path is a plane curve. So pretty much you need to be able to write x and y as those continuous functions. If you recall, a continuous function has to have no gaps, no holes, no jumps, no skips. You have to be able to trace it without lifting up your pencil from your paper. So what we're going to do is we're going to practice sketching a plane curve. So drawing a plane curve if you are given your parametric equations. In order to do this, remember we have these three values that are now connected. We have a t value that connects to a particular x and y value. So what we're going to do is we're going to choose t values. Those are our new inputs for both the x and y equations. We're going to pick t values, and we're going to find x and y values that correspond. We're going to find those coordinate points that correspond to t values. And when we graph these, we're going to graph them in the order that the t value is increasing. So a lot of times, especially if our t value is corresponding to time, like we were dealing with back here, t value had a time connection, we start at 0 and we increase. So I start when t is equal to 0, we're at this point down here, and then as t gets larger, then this is our second point, and our largest t value is this third point right here. So you can see we have these arrows telling us in what direction we are moving. Parametric equations and plane curves have a direction or an orientation that goes along with it. So going from left to right is going to be different than going from right to left. Going in a clockwise direction or a counterclockwise direction are going to be different from each other. So we match the order to the t values that are increasing. So t's typically start at 0. They do not have to. In this example that we're going to sketch right now, we have two equations. We have our x equation, x is equal to t squared minus 4. And we have our y equation, y is equal to t over 2. And our t value doesn't start at 0 anymore, but rather it starts at negative 2. And we're going to go all the way from negative 2 up to t is equal to 3. So the way that we want to sketch this curve is we want to start by building a table. We want to build a t, x, y table. I'm going to pick t values. We're going to find corresponding x and y values. And then the way we're going to find those x and y values is just by plugging them in. So what we want to do is we want to start with the lowest t value that we can. So we're going to start at t equals negative 2. If we substitute that into the x equation, we get 0 back. Substitute in the y equation, we get negative 1 back. And then you can jump in t values by almost any step count that you want. You can go up by 1s or by 2s. Typically, we like to go by 1s unless we have a much smaller window or a much larger window. So this is negative 2 to 3. That's a fairly good size. So we're going to just go up by 1s. If this was like a negative 2 to negative 1, we might want to go up by quarters. Or if this is like negative 10 to positive 10, we might go up by 2, something to make it a little bit more manageable. But if I substitute a negative 1, we get negative 3 back for x and negative 1/2 for y. Substitute in 0 for t, we get negative 4 for x, 0 for y, and we can keep going. And if we were to keep going, we would end up with this table back. Okay, so you pick specific t values, substitute them in, you get your x and your y values back. And then these right here, these are our points that we're going to plot. We're not plotting t points. There's no t axis on our graph. It's only the x and y axis on our graph. So we're going to graph our x, y coordinate points, but we're going to graph them in the order of our t values. So starting with the lowest t value and moving up. So if we do that, we end up with this graph right here. And as I go through and I plot those XY coordinate points, I do want to label those points with the t values that they go along with. So if I start, that t value is equal to -1, that's our lowest one, that's the first point. And so I don't necessarily need to label the XY coordinates, but I want to label it as this is the point where t is equal to -2. Because there is no t-axis, when I label those points, I want to label the t value that goes along with them. And then as I move along, I have t equals -1, and then t equals 0, and t equals 1, and t equals 2, and then t equals 3 at the end. And you can see the direction, the orientation that our curve has. It's somewhat of a clockwise orientation. You can see this is a parabola. Now, if we go back to this set of equations, you may not necessarily think that that is a parabola. You can sort of see that it's got a parabola-like shape, but it may not have been obvious to you. But once we graph it, you can see, yes, that's a parabola. It's a parabola that's opening to the right. And one other thing I want to note is we do not have arrows on the ends. Those are endpoints at t equals -2 and t equals 3 because t is restricted from -2 to 3. It does not go past that. My graph cannot go past those points. The x and the y equations are not defined for t values outside of -2 to +3. So we do not go past those. They have a starting and a stopping point. So this is a piece of a parabola, not an entire thing. This is not the only set of parametric equations that can graph this curve. So every curve, almost every curve, has more than one solution, more than one set of parametric equations that you can use to represent that. If I look down, the one on the left, that's the one we just graphed with the equations we were looking at before, but the one on the right, that is the same curve, but we have a different set of parametric equations, which means we had different t values. If you look down below, that first point is no longer when t is equal to -2, that's when t is equal to -1. And then our last point is that t is equal to 3/2. So my steps, if you notice, my steps are going up by half a value. T's are increasing by 1/2 each time instead of increasing by 1. And so the t values, the range is smaller. I go -1 to 3/2. So when we have those smaller steps, when we have a smaller range for t values, we say that we are increasing more rapidly. It's moving faster. So if you think about two people are walking along these paths, and think about t as a time, which is a little weird because of the negatives, but if we can just think about it for a time for a second, one person on the left is walking from -2 to 3 along the path, and then the second person travels the same path, but they don't start till -1, and they end up stopping at 3/2. So they're moving more quickly, they're moving more rapidly, but they are still covering the same curve. All right, what we're going to do right now is we are going to kind of go backwards from what we just did. We're going to eliminate the parameter. So when you're asked to do this, you're typically given a set of parametric equations, and then you are asked to eliminate your parameter. Essentially, let's go backwards and let's write this as a rectangular equation. Let's go and put this into something that's a little bit more familiar to us. So the way that we tend to do this is you want to eliminate your variable, one of your variables. So by looking at your two equations, x equals t squared minus 4 and y equals t over 2, we want to get rid of t and get this into equation of just x's and y's. So take one of your two equations, solve for t, and then substitute into the other equation. So if I look at the two equations that I have right here, I'm going to look at this second one. It's a little bit easier to work with. Oops. We're going to solve for t. So instead of writing y equals 2 over t, t then has to equal 2y. But that means for every t value in the x equation, I can replace that with 2y. So I get this equation here, x equals 4y squared minus 4. I'm going to get rid of that. There we go. And I've eliminated my parameter. So you can much more quickly see that this is indeed a parabola. It's opening to the right. We did lose the connection to our time, but sometimes it's a little bit easier to work with this. It all depends on what you're trying to do, what you want to use these equations for, and which one is going to be a little bit more helpful. So we're going to practice. We're going to sketch this curve that's represented by equations, which are not super pretty, but they are parametric equations. Both x and y are written in terms of t. But we're going to do it by eliminating our parameter. So we're going to go back to a rectangular equation. We're going to connect this to just x's and y's. And before we do that, I want to do a quick little note. If you look here at your two equations, x and y, we do have restrictions on t values, even though they aren't specifically stated, they aren't explicitly written. We do know just by the domain of these two equations that there's going to be a t restriction. So I know in the second one, my t value cannot equal -1 because I would have a division by 0. But I know in the first one that t has to be strictly greater than -1. So altogether, I know that my t value has to be strictly greater than -1. So I just want to keep that in mind. We're going to get back to that in just a second, but I just want you to keep that in the back of your mind. So the way that we want to do this is we want to look and say, okay, just like before, we want to take our two equations. We want to take one of the two equations and we want to eliminate our variables. We want to solve essentially for t. In this case, it's easier to take the more complicated one because we're going to have to do a substitution. So you want to kind of think a little bit further ahead. Say, okay, if I'm looking at these two equations, I am going to have to substitute in for t into one of those equations. Whichever one I don't solve for t in, I'm going to have to substitute. So I'm either going to substitute t in here and then try to simplify, or I'm going to substitute in here and here and try to simplify. It is going to be a lot easier to simplify this equation than it is to simplify this one because of that square root. So you want to sort of try and think through a little bit, which one do I want to simplify? Which one do I want to solve for? So we're going to take that first one, that x equals 1 over the square root of t plus 1. And I want to solve that for x. So I'm going to start by just squaring both sides. We're going to undo that square root, get rid of that square root. We're going to square both sides. So x squared has to equal 1 over t plus 1. And then by doing some algebra, by multiplying both sides by t plus 1, we get x squared times t plus 1 equals 1. So x squared times t plus x squared equals 1. And we can keep solving, and we end up getting t equals 1 minus x squared over x squared. Okay, so by taking this, subtracting, and then dividing, we get 1 minus x squared over x squared. Now I want to take this, and I want to substitute it into the y equation. Both places I have the t. And do you see how this is going to be a little bit easier to work with than trying to substitute into the square root? So I do that. It's not a very pretty equation, but we can simplify. I think the best way to simplify this is going to be, let's try and get rid of some of our fractions. All right, so let's take our equations and let's multiply both the numerator and the denominator by x squared. Let's cancel some fractions. All right, that's going to simplify the numerator, make that just 1 minus x squared. And then it's going to make that denominator 1 minus x squared plus x squared, because think about it, this right here needs to multiply by that fraction and by 1. But then that's really nice because look at your denominator. If you simplify your denominator, you get 1, just 1. So then we get our y is equal to 1 minus x squared. So we have this wonderful equation, y equals 1 minus x squared. It's a rectangular equation. It's much nicer. It's much more easily identifiable as a parabola. We can even go further and we can put this into vertex form, what we've been talking about before spring break. Y equals a times x minus h squared plus k. Just do a little bit of rearranging, that y equals negative x minus 0 squared plus 1. So we have this rectangular equation. It is a parabola. It's going to open downward, has a vertex up at 0, 1. Now, way back at the beginning, we talked about how t had a restriction on it. We said that t had to be greater than or equal to -1. That is going to put a restriction on our final equation. Because if I have t values that have to be greater than or equal to -1, that's going to have restrictions on my x's and on my y values. Okay, so this is not going to be a full parabola, but rather it's only going to be a part of a parabola, either half or a quarter or some section of a parabola. So we want to think through, okay, if my t value has to be greater than -1, okay, what's sort of the lowest value you could have for your x? All right, so I can't put -1 in for t, but I could put in like -0.5. Or I could put in -0.9 or -0.999. If I did that, the denominator is getting really, 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 really small. If your denominator is getting really, 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 really small, what is your x value getting really, 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 really close to being? Okay, think about 1 over the absolute tiniest number that you can think of. That's going to be a really, really large number. So as t is getting close to -1, our x value is going to be getting really, 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 really big. It's going to go off to infinity, which is great. We like our x's going off to infinity, but that doesn't really help me with the restriction. So I have to think about the other endpoint for t's. T has to be greater than -1, which means t can go off to be as big as we want it to be. If t can go off to be as big as we want it to be, if we can put in, say, 1,000 or 1,000,000, I think that's 1,000,000, yep, or 1,000,000,000 or 1,000,000,000, or it just keeps going off and off and off, then this entire denominator ends up getting really, 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 really large. So then I have 1 over a really, really big number. Think about 1 divided by the biggest number you can possibly think of. That's going to give you an absolutely tiny number back, which means as t goes to infinity, my x value is going to get closer and closer to 0. So that's giving me a restriction. My x value can never be negative. Think through the values that you can get back from x from this equation. No matter what values you put in for t, as long as t is greater than or equal to 0, my denominator is going to be positive. And my 1, my numerator is positive. So positive over a positive, that's always a positive. So my x value is always going to be positive. So x is going to be greater than 0. It's never going to equal 0, but it's going to be greater than 0. So that gives us this restriction on our parabola. My domain for x is restricted to positive values only. And when I go to do that graph, you can see how there's now an open circle when my x is equal to 0, because x is never going to actually be 0 based off of the parametric equation that we're given. This equation here is never going to actually be 0. But it's going to get really, really close to 0. As t gets really, 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 really big, it's going to get really, really close to 0. So you can see when t is -0.75, and then t is equal to 0, and then t is equal to 3, we're moving up the parabola now. So we have that sort of counterclockwise orientation. But it does. We have that domain restriction that came out of the restriction on our t value. Again, there are multiple ways that you can write your parametric equations. There is always the trivial way. So you can take the original input equation or that original input variable. In this example, y is my input. And you can always make your input value just equal to t, and then x has to be equal to the equation that you have. That's the easiest way to turn something into a parametric equation. Not the most exciting, but it's the easiest way to do it. You can do anything else. You could say, okay, let y equal t over 2, like we have in this example here, and then substituting that into this equation, you get that t squared minus 4 back. So, x equals y times, oops, not y, 4 times t over 2 squared minus 4. That's going to simplify to x equals t squared minus 4. And we get that same parametric equation back. All right, what we're going to do is we're going to look at some parametric equations that don't involve t, but rather have some trig equations. When you have parametric equations that have trig equations, trig functions, sine, cosine, tangent, eliminating the parameter isn't always so straightforward. You don't necessarily want to solve for your parameter anymore. You can try and do that. If I try to do that here, I get theta equals cosine inverse of x. Then I have to deal with the restrictions on cosine inverse. But then I go over here and then I get y equals sine of cosine inverse of x. And that does not look very pretty at all. So typically when you have sines, cosines, tangents, what you want to do is you want to look for identities. Identities are going to be your friends. Now, we're not doing those identity proofs, but we want to look for identities. And particularly if you have sine and cosine, you want to use the Pythagorean identity of sine squared plus cosine squared equals 1. So if I look at my x equals cosine theta and y equals sine theta, to get at sine squared plus cosine squared, or cosine squared plus sine squared, what I want to do is, okay, that means x squared has to equal cosine squared theta. Y squared has to equal sine squared theta. So if I take x squared and I add y squared, that's cosine squared theta plus sine squared theta. Well, that's just telling me that x squared plus y squared has to equal 1. And that's a rectangular equation that we know. That's a rectangular equation we know how to deal with. X squared plus y squared equals 1. That's just a circle. So generally, if you have a cosine theta and a sine theta with your x and your y, that's going to connect to either a circle or an ellipse or some other closed curve. All right. If I look at this next example down here, x equals 3 cosine theta, y equals 4 sine theta. This is a little bit trickier, not too much more difficult, but if you start by just squaring both sides, you might see there's a slight issue. How am I going to get sine squared and cosine squared without coefficients? So before you square it, what I would do is I would actually divide. X equals 3 cosine theta says x divided by 3 has to equal cosine theta. And then y divided by 4 has to equal sine theta. Now if you square both sides, x squared over 9 equals cosine squared theta. Y squared over 16 equals sine squared theta. Well, that's going to give me x squared over 9 plus y squared over 16. That's equal to cosine squared theta plus sine squared theta, or x squared over 9 plus y squared over 16 equals 1, which, while it's not a circle, is an equation, is a function that we know how to deal with. I'm sorry, that's not a function, but it is a conic section that we know how to deal with. It's an ellipse. All right, so parametric equations are really helpful in connecting our x and our y values to a third variable, a third parameter, typically time, or in this case with theta, an angle value. And it takes the equations, the functions that we're used to seeing, and we start to look at them in a slightly different